To the introduction to basics of chemical kinetics. My name is Imtiaz, and I will be speaking on the webinar today. So the agenda for the webinar is that we'll start off with, again, the welcome and the introduction, a little bit about myself and a little bit about chemical engineering life. And then we'll jump directly into the foundation of chemical kinetics. Leading up, we'll have a look at some of the factors that affect the reaction rate, and we'll talk about why they affect the reaction rate and what's the science behind it. And then having understand the foundation, then we'll have a look at the mathematical models in kinetics, looking at the first order reaction and the second order reaction. And then we'll conclude everything by looking at the relevance of kinetics in the industry. And if anyone has any questions, then you're more than welcome to ask them at the end. During the webinar, I would truly appreciate if you all could be muted. If you may have a question, feel free to just unmute yourself and ask me if it is. So, my name is Humzaa, and like I said, I am a chemical engineer myself. I graduated with my master's back in 2020 from the Technical University of Denmark, and since then I have been working in the pharmaceutical sector here in Denmark as well. And I also happen to be the founder of Chemical Engineering Life. Chemical Engineering Life is an online platform for chemical engineers all around the globe. It's a place where the idea is where we would like to help young students, graduates, network with other experienced professionals, and also be able to ask questions regarding their career and make some informed decisions about what they would like to do with their chemical engineering degree. There are a lot of things that we do. The very first one, we have different talks with different chemical engineers. We have them in paper form, and we also have a podcast called Decoding Chemical Engineering, where we talk with different chemical engineers working in different sectors. We try to get as much knowledge as we can about what chemical engineers are doing in different areas, let it be in the pharmaceutical, petrochemical, and what sort of everyday life it is out there for young graduates. We also have webinars like this one with different professionals where we'll have a look at both engineering topics and non-engineering topics. And the same goes for our online courses, where you can find different courses related to programming, Excel, basic chemical engineering principles. But majority of our courses are focused on the stuff that you may not necessarily have learned while you were at university. So that's what we are aiming for. And finally, we have a global mentorship program. The mentorship program is a program that allows us to connect young individuals with the professionals so that they can ask the right questions to the right people. Because most of the time, it can be quite overwhelming to figure out what you want to do with your career and where you want to work, what industry, what role, and so on. So it's always a good idea to speak with the people that have walked that path, so that you can ask them the question and they can share their experiences with you. So that's what our program is all about. So far, we have had almost more than 500 participants joining us from 13 different countries. So it's been a huge success, and so far we have been very happy that we were able to help as many graduates as we could. And apart from these, we also have a place called Chemical Engineering Chronicles, where we publish different articles about chemical engineering and how chemical engineering impacts our everyday lives. We also have multiple entertaining video series, which you can find on our YouTube channel, where we talk about chemical engineering in an entertaining way, and also in a more informative way, so you can learn more about chemical engineering. And finally, we have an online forum at the website where you can go and you can raise your questions and also answer the questions that have been raised by other chemical engineers. So this is a quick summary of what we're doing over here at Chemical Engineering Life. And to answer the question where you can find us on YouTube. We have a YouTube channel where you could go and join the community and watch our video series, our podcast, our past webinars as well. You can follow us on Instagram, where we post some funny posts about chemical engineering and jokes, and we share our insights from the interviews that we have conducted. You can become a free member on our website already today at www.ChemEnggLife.com. And by becoming a free member, you can interact with all the other members. You'll be the first one to know when a new webinar is coming out, a new course is coming out, and you can stay updated on our latest initiatives and our latest news in chemical engineering. And finally, you can also connect with us on LinkedIn. where you can connect with many other chemical engineers that we have connected with, and you can make use of our network to talk and learn and connect with the other fellow chemical engineers working in different areas. So, but you can learn more about us if you visit our website at www.ChemEnggLife.com. And if you may have any questions or any doubts, or if you would like to learn more about about our mentorship program or our webinars or courses, but you're still in doubt about what to do, you're more than welcome to reach out to us on the website as well. So that was all about me and the chemical engineering life. So now starting off with the foundations of chemical kinetics. So the very first question is, what exactly is chemical kinetics? Chemical kinetics, very simply, is the study of reaction rates and the factors that influence them. So for example, let's say you have a reaction, chemical kinetics would tell you how fast that reaction takes place and what can you do to either, optimize it better or minimize the byproducts in any way. Uh, it is important for you to understand how fast these reactions occur, because sometimes you would like to control them, you would like to control the variables, you would like to optimize them. Sometimes you would like your reactions to go to 100% completion. That's where chemical kinetics can tell you. At the same time, you would like to know how reactions proceed over time. It could be, for example, like the climate change, ozone layer, the effect of ozone layer. We would like to know how quickly that reaction takes place and how can we mitigate or make the reaction, like we can make it minimize the reaction time with that as well. And obviously, in industrial and research settings, having this information is crucial because, like I said, there could be a lot of reactions today where we would like to optimize the reactions and the product output as much as possible. So that's like a very basic, explanation of what chemical kinetics is. And before we begin, there are some terms that you would have to be familiar with. The very first one is a reaction rate, and you'll hear me using these four words, and we'll actually jump in detail later as well what each one of them mean. But very briefly, a reaction rate, that's basically the speed at which reactants are converted into products. A rate law, that is a mathematical expression that links the reaction rate to the reactant concentrations. Then we have a rate constant, and that is a constant value that tells you about how fast a reaction occurs, and it is proportionally constant in the rate law, and it depends entirely on the temperature. And then you have something called an order of reaction, and that is the sum of powers of the concentration terms in the rate law. And more on that later. I know it's a bit confusing, but in a minute, all of it will make sense. So the very first thing that, I'll just update your memory is that when you have a chemical reaction, you have reactants and you have a product. In any sort of chemical reaction, your reactants, they get used up and you start producing your products. So over time, if we plotted a graph of concentration over time for a specific chemical reaction for our reagents and our products, this is something that it would look like. Over time, the reactants would start to reduce, the concentration of the reactants begins to reduce, and the concentration of products starts to increase up until the point when all of the reactants have been used up. At that point in time, no more products are being produced because you have used up all of your reactants. Uh, Many times you could assume that you have 100% conversion. 100% conversion would mean that all of your reactants would get used up. Does not necessarily happen in the real world. In real life reactions, you will always and always have a small amount of reactants left behind, and then you would have to remove in your downstreaming. But if that's the case, then you would end up getting in the output stream, you would end up getting your products plus a specific percentage of your reactants that has not reacted to produce the product. And then we would write that up in terms of a chemical reaction that would look somewhat like this. So you have A plus B is equal, and that yields C plus D. So your A and B, those are your reactants, and C and D, those are your products. The capital letters that you see on the screen, they are your reactants and your products, and the corresponding smaller letters, the small a and small b, and the small c and the small d, they are something that we call a stoichiometric coefficient. Now, for this specific reaction, a plus b is equal to c plus d, if you were like to convert that, if you would like to explore that further, then you have your reaction rate. The reaction rate is defined as per the equation that you see on the screen. It is 1 over the stoichiometric coefficient multiplied by the differential of that concentration divided by time. Because how do you define a reaction? Like I said, if I go back to the graph again, if I asked you, how do you know that a reaction is taking place? Well, you know because the reactants are being used up. So your reactants would start to reduce and your products are being formed. We write that up in mathematical language that is written in that manner as a differential, where D, the square brackets means concentration, and the A written in the bracket means the concentration of A, the molar volume of A, divided by dt, t, the small t, that is time. So that differential simply means the change of the concentration of A over the change of time. And then uh, and if you write it for the reactants, it is a negative. The reason it's a negative, the differential is negative because it is being used up. So the differential, if I was to plot it, the slope of it is negative. On the other hand side, the differential for your products is always going to be positive because your products are being formed. So if I go back and if you look at this curve one more time, if I was to calculate the gradient of the curve at different points, that is, and if you remember, that's basically what the differential means. That is merely the slope of the curve. You'll see that it is the steepest in the beginning, and as it goes to the bottom, it becomes linear and linear. That means that as soon as you hit a plateau, that's when you have reached the maximum production point. Here, so that the first line, that is your reaction rate. Then you have the rate law, and that was the mathematical expression that links your rate constant with the concentrations, and that is written up in that manner. So that's k, small k, the rate constant, multiplied by a to the power of n, b to the power of m. The n and the m, they are your powers for the concentrations, and they define the order of reaction of your chemical reaction. Now recall that I said that obviously most of the time we assume that there is 100% conversion, but again, that's not entirely true. There will always be a small amount of reactants left behind. So in a very true sense, your rate law should look something like this, where you have the reactants minus the Kr of your products. Uh, but obviously, if your Kr is very small, then the rate law is always written in terms of your reactants, because those are the ones that are being used up. So we're always interested in knowing how much of the reactants are being used up. Um, and then the sum of the powers of these concentrations that you see in rate law, that means the n plus m. If you sum them up, that is something that we call the order of reaction. And we'll speak more on that later, actually. So even if it's a bit unclear now, it will definitely be a lot more clear to you after a few slides when we'll dig deep into the first order reaction and the second order reaction. But right now, this is basically the basics of kinetics and the basic terminology that you have to keep in mind. And then we're coming down to the collision theory. The way reactions take place is that we all know that we assume that there are small particles who are spherical, and they have no they're not attracted to each other, and they are freely they're free to move around in the confined space that we have for the reaction. What happens is that imagine that you have two different types of particles flying around in a small box, right? As the two molecules of the two reactants, let's say A and B, they would have to hit each other in a very specific position and a very specific amount of energy to be able to form the new product. So for example, let's say we have a reaction of carbon dioxide with oxygen, and that forms carbon monoxide. Then the carbon dioxide molecule would have to hit the oxygen molecules in a very specific correlation, in a very specific direction, and they have to hit each other in a very specific amount of energy. And as soon as they do, that's what we call a successful collision. And that successful collision is then allows us for a reaction to take place. And the minimum amount of energy that the particles need for that successful collision, that is something that we call the activation energy. So just like you see on the screen on the right, you have multiple particles flying around, small spherical particles flying around, and then they would have to bump into each other in order to get a successful collision. And that's exactly what the collision theory looks like. And the collision theory basically finds itself at the heart of your reaction kinetics. The more the collisions take place, the faster your reaction rate. The slower the collisions take place, the less the probability of the collisions taking place, the less your reaction rate. So it's all about the particles hitting each other in exactly the same orientation and with the same amount of energy. So as you see on the screen, if they collide without the activation energy, then you see the A and B, there's no reaction at all. But if they collide with the required activation energy, that's when a reaction has taken place, and now you have new particles coming out on the other side. So the collision theory is the very fundamental theory behind why and how reactions actually do take place. But then having a look deeper at the activation energy, because uh, the main factor that would allow the reactions to take place, that is the activation energy. We all know that when the particles are flying in the air, they have something called a kinetic energy. That means that they are moving around, the energy of movement, that is kinetic energy, right? So the particles actually have kinetic energy. If the activation energy is higher than the activation energy of the particles, then your reaction would actually, the reaction rate would be slow. If the activation energy is less than the kinetic energy of the particles, well, then the reaction rate will be strong. So the whole idea is that the particles have to meet up with that activation energy requirement. And if you were to plot that in a curve, that would look somewhat like this that you see on the right. So for the reaction of A plus B is equal to C plus D, you have your A and B. The sum of the kinetic energy of A and B would actually would have to meet up the activation. Would have to be equal to the activation energy of the reaction. And as soon as something reacts, as soon as you have A particles and the B particles, they hit each other, the sum of the kinetic energies A and B, they take it up to the transition state. The transition state is actually is a place where you have the highest energy in a chemical reaction, and it's a very unstable place. Where you mostly have the radicals, and it doesn't last very long either. And that's the place where your products are actually formed. And that's something called the transition state theory. We're not necessarily going to look deep into this one, but the idea is that the particles react, they go up to the higher state, the transition state, they react, and the difference between your particles and the transition state, that is what we call the activation energy. As soon as your products are formed, then you'll notice that then it starts to go down, and the products, the activation energy, the kinetic energy or the potential energy of the products then is less than your starting reactants. And the delta H, that is just a change in enthalpy between your reactants and your products. And the sum of the activation energy and the enthalpy, that would be the energy that you would have to provide to the system in order to go from the products back to the reactants if it is a reversible reaction. And obviously the energy that you lose between going from your going from your reactant to your product, that energy is given back to the reactant so that the other particles may have the same amount of energy to be able to reach the transition state. So that's actually how a reaction takes place. That's the very basic science behind it, that you have your kinetic energy. The kinetic energy allows the particles to collide with each other. The particles then get moved up to a transition state. They react. It's a very unstable stage. And then by losing the energy, sending the energy back to the reactants, they then go down to your final product stage. Uh, and the energy can be described, and the entire theory can be summarized by the Arrhenius equation. The Arrhenius equation relates your rate constant with the activation energy and your temperature. As you see on the right, the K, that is your rate constant. The capital A, that is the frequency factor. That's a constant value. Then you have E, that is just the constant. The capital E with the subscript A, that is your activation energy. The T, that is the temperature in kelvins. And R, that is the ideal gas constant. So that is something that we call the Arrhenius equation. And if you see on the left, if you can see that you can plot your kinetic energy as on the other side of the fraction of molecules that are interacting. So if you increase the temperature, of your system, then obviously remember that a temperature is the measure of the kinetic energy within of your particles. So that if the temperature is higher, that means that there is more kinetic energy in your particles, hence a much higher probability of collision. And therefore, more and more particles will then be able to have enough energy to meet the activation energy, and hence your reaction will be a lot faster. And that is why temperature is one of the most important factors that affects your rate constant and your reaction rate. Now, the Arrhenius equation can actually be used to plot something called the Arrhenius plot. And it's actually derived directly from this expression. If you take the natural log of the entire equation, you can end up you will end up getting something that looks like this. And if you look at the expression, the ln k is equal to the first term plus ln of a. It resembles your the equation of a linear curve. Y is equal to mx plus c. The m is the slope. The c is the y-intercept. And if you plot that equation onto a graph, if you plot your ln k against 1 over temperature, you end up getting a curve that looks like that. So you can actually use this expression. If you have the k value, you normally get the k value from the experiments, from performing experiments. So if you have the k value and you have the different temperature values, for example, let's say you perform 5 different experiments at different temperatures, and you calculate your k value for each experiment, you can then plot that on a curve and your y-intercept. Then you can calculate your the a value, and you can use the slope to calculate your activation energy of that specific reaction. That's not something that you can just figure out mathematically, but that's something that we perform experimentally. So you perform the experiments at different temperatures, at different k values, for different rate constants, and then you use the slope to calculate your activation energy and the y-intercept to calculate your a value. And we actually have an example that you see on the screen here for the decomposition of hydrogen iodide into hydrogen and iodine. So for example, if you look at the first two columns, sorry, we have different temperature values in kelvins, and we have the respective k value that we have experimentally figured out at each temperature value. The first thing that you do, you take the reciprocal of temperature, that's 1 over T. As you can see, I've done that in the third column. And then you take the natural logarithm of K that I have done in the fourth column. Then you plot your third and the fourth column using Excel or any other mathematical program. And then you see that we end up getting a straight line. From that straight line, coming back to the expression like this one. So if it is analogous to the linear curve, y is equal to mx plus c, that means that the slope must be equal to negative EA divided by R. And that's what we do. So negative EA divided by R is equal to the slope. We throw in the slope value, and we know that the R, that is a constant, the rate law, 8.314. And then you can easily calculate the activation energy of any reaction, given that you have the experimental data. Just remember that this gas constant, ideal gas constant, this R value, it can be a bit tricky. The reason it can be quite tricky is because it has multiple different values based on the units that are being used. So pay extra attention that you're using the correct units in your experiments and in your calculation. It's very common to make a mistake. Like, for example, this value of 8.314, it's based on kelvins. So if you get a question where the temperature is provided in Celsius, remember to convert that into kelvins. If you don't, you'll obviously end up getting the wrong answer. And the same goes for joules, for example. I mean, you already may know it yourself. Sometimes during exams, the professors, they do tend to give you the data in Celsius. Sometimes you're given the energy in kilojoules, so you have to remember to convert that into joules before you can use the ideal gas law. But that's just a reminder. Remember to use the correct values. And the thing is that imagine that you don't have 5 experiments. You can't plot the Arrhenius plot. So instead, you can convert this into the integrated Arrhenius equation, in which instead of using 5 values to calculate the activation energy, you can merely make use of 2 experimental values. So if you have, let's say, T1 value and T2 value, and you have the corresponding rate constant for T1 and T2, then you can actually make use of this equation as well. This is obviously not as specific as the first one, but it still gives you a very good value for the activation energy. So regarding the activation energy and the Arrhenius equation, you can make use of these 3 expressions. The first one, that is the very basic Arrhenius expression. You can, if you take the natural logarithm of the first one to get rid of the E, the natural E value, then you get the second one. But if you integrate it instead, then you actually end up getting the third one. And all 3 of them can be used and are used depending on what information you have in hand. And again, like I said, they could be used to calculate your activation energy based upon your experimental data. You could get an equation to ask you about you could be asked to calculate the T value. You could be asked to calculate any other variable that may be missing in experimental or in a kinetic problem. So that was the very basic introduction to what kinetics are, and I hope the idea is clear now, especially the collision theory, how reactions take place, and what exactly is happening behind the stage when we say that the reactants are reacting. They're basically just colliding with each other. And then you probably now have a better understanding of what activation energy is and the expressions and how it is described based on the Arrhenius expressions. But very briefly now, we'll have a look at the factors that affect the reaction rate. There are multiple, because now, as I've said, that how reactions take place is merely just a collision path, right? You have multiple particles, they are colliding with each other, and if they collide with the specific amount of energy in the right orientation, and voila, you have your product. So the idea is that we would like to affect the probability of collisions as much as possible, right? The very first factor that comes in mind, that is temperature, because the true definition of temperature is actually the measure of kinetic energy of the system. So therefore, that means that if I increase the temperature of the gas or of any other reactants, that means that now the particles have a much higher kinetic energy compared to a lower temperature. If they have more kinetic energy, they are moving around a lot faster. That means that there's a higher probability of collision. And secondly, they have more energy to collide and reach the activation energy stage. So that means the first factor, that is temperature. The second one is the concentration of the reactants. Now, obviously, and I'll actually dig deeper when we come to the slide of the concentration, but the idea is that if there are more particles in a smaller space, that means that there is a higher probability that they will collide with each other. I mean, imagine that you are, in a room with two people, and you are in a room of, let's say, 50 square meters. Obviously, the probability of you hitting the other person is very low. Now imagine that you cram 100 people in the same room. Now it will be very difficult for you to move around without colliding into anyone and someone else, right? That's the same theory that we would run if we increase the concentration of the reactants. And then if you have gas reactants, the way we can increase the concentration is by increasing the pressure. But these three factors, they directly affect the collision theory. We have another variable, and that was the activation energy. So instead of us increasing the probability of collision or providing more energy to the particles to reach the activation energy stage, we can make use of something called a catalyst. And a catalyst takes a shortcut, and it does so by reducing the activation energy of the reaction. Hence, that even if the particles do not possess the right amount of kinetic energy, they're still able to reach the transition state because the transition state requirement has been reduced. And that's exactly what a catalyst does. So the very first one, like I said, temperature. And a very good example of temperature affecting the reaction rate is you leaving your food on the kitchen counter. If you leave your food on the kitchen counter, it will spoil a lot quicker, right? That's something that we all know, something that has happened to all of us. But if you leave the same spaghetti in the refrigerator, then obviously it does not spoil at the same rate as it would have if you left it on the kitchen counter. So temperature, that's another example of reaction rate, because within the refrigerator with a lower temperature, the rate of spoilage is reduced by a lot. At the same time, in laboratory experiments, if you put a boiler under the reaction, under a specific test tube, it does react a lot faster. Generally, it has been said that if you increase the temperature by 10 degrees Celsius, it will approximately double the rate of a reaction in a homogeneous system. So that's actually quite a lot, right? And that is a very basic fact. The chemical reactions typically occur faster at higher temperatures, but there is still a trade-off. And you have to be careful because some reactions, they only go one way, right? You put something together and you heat it up, and your reaction will go quicker to the other side. It will react a lot faster. Imagine, and that is also true for reactions that are endothermic reactions. On the other hand side, imagine if you have a reaction that is exothermic. Exothermic means that that instead of taking in energy, your system is actually releasing a lot of energy. And in that case, you'll see that the products tend to be, and if you look at this plot, that would be an example of a endothermic reaction. For your exothermic reaction, the products would actually be at a higher stage than your reactants. After a certain point in time, if you are heating up that reaction, you would still achieve a quicker reaction rate, but after a certain amount of time, increasing the temperature of that reaction would actually start to favor the reversible, instead of going from reactant to product, you will start favoring the product towards the reactants. So therefore, when you're talking about equilibrium reactions, you always have to keep in mind whether or not your reaction is endothermic or exothermic. But in the very basic, the rule of thumb is that if you do increase the temperature, then your rate of reaction would be a lot faster. With the exception that if you reach a certain point of the temperature, then you would actually be in a way reducing the yield of your reactor. So you have to find the balance between the two. But in terms of purely on based of kinetics, the higher the temperature, the more the kinetic energy, and hence more particles now have temperature and have the energy to cross the path to the transition state. If you look at the pressure, if you have gas reactants, as you see on the left side, if it is lower pressure, that means that there are fewer collisions, a fewer probability of collisions. If the pressure is increased, then there are more successful collisions because now you have more and more products crammed up in the same space, and they also have more energy to move around. And also remember that based on the kinetic theory, the kinetic energy is actually related to the pressure as well. So as you see on the screen, on the formula below, so that means that if the pressure is increased, then the kinetic energy is also increased, and that is supported by the kinetic theory itself. The same is true for concentration. And the example that I gave earlier, that there are two people in a room of 100 square meters, the probability of them colliding head-on into each other, that's very low. But if you are now crammed with 100 people in the same room, then obviously you'll start hit you even without your choice, you collide with everyone in that room. So that's the same theory behind increasing the concentration of reactants. Finally, the catalytic reaction reduces the activation energy of your reaction. As you see on the screen, the blue curve, that is what your reaction would look like if you did it without a catalyst. But if you use a catalyst, then the catalyst shows you the term is that it takes you to an alternative path for a reaction to take place. And your transition state is reduced, your activation energy is reduced. So therefore, now you don't need that same amount of energy to be able to react to produce your product. And that is why we use a catalyst. And catalysts are used quite a lot throughout the industry. The catalyst, like for example, the Haber process, which produces ammonium, they make use of catalyst. Without a catalyst, we would actually have to add in a lot of energy to provide the energy to reach the activation energy. A catalyst allows you to firstly speed up the reaction by providing a small activation energy, and you save a huge bank on utility and all the other expenses that might come with having a proper for the experiment. So that was all for the factors and the basics. Now we'll jump directly into the mathematical model in kinetics. So the very first term that you have to understand is something called a molecularity. And the molecularity of an elementary reaction is the number of molecules that collide during that step in a mechanism. If there is a single reactant molecule, then that step is called unimolecular. If there are two reactant molecules, then that's something that we call a biomolecular. And if there are three, which is actually quite rare, then that is a termolecular. And we have not really ever seen, it is very rare to have more than three reactants interacting, colliding with the correct orientation with the same energy. So typically we always have either unimolecular or we have something called a biomolecular. So if you see on the screen on the top, for example, if you have your reactant A, which is a single reactant, and that is being converted into your product, that is something that we call a unimolecular. And the rate law for that would look something like this, that is equal to K times the concentration of A. On the other hand side, you have your A plus B, that makes a product. Now you have two reactants that are responsible for the final product, and that is something that we call a biomolecular. So for example, if you take this equation of nitrogen dioxide reacting with carbon monoxide to produce nitrogen oxide and carbon dioxide, the only way to figure out the order of reaction is by experimentation. So without experiments, we don't know. There is no mathematical way. There is no other way to figure out that if it is unimolecular or biomolecular or termolecular. And the way we figure it out is that you perform an experiment in which you put in one box, you put in your nitrogen dioxide and you put in carbon monoxide. You perform the first experiment, you perform the second experiment in which you double the concentration of carbon dioxide, and then you see how much does that affect your final product output. Then you perform an experiment in which you double the concentration of carbon monoxide, but you don't touch nitrogen dioxide. And then you see how does that affect your final product output. And then let's say that doubling my nitrogen dioxide quadruples my product, then that would mean that the reaction is second order with respect to nitrogen dioxide, and that's what's written on the screen as well. That is why we write a power of 2, because if I double it, my product is quadrupled. On the other hand side, if I increased my carbon monoxide, if I doubled it, and it has no effect on my output, product output, then we say that carbon monoxide, it is to the zero order. Zero order means that it literally has no effect on our product output. We still need carbon monoxide. We still need carbon monoxide for the collision, for successful collision, but the rate of the reaction has nothing to do with carbon monoxide. Like I could increase carbon monoxide a great deal into the reaction, and it would have no effect on the actual reaction. So the defining concentration or the defining reactant that decides how much product is being produced, that would actually be nitrogen dioxide. That's the idea that we try to get out of our experimental data. So for a first order reaction, that would mean that you have your one reactant, and that one reactant is dependent on the reaction is dependent on that one reactant for your product. So the rate law for that reaction can be written into something that looks on the screen. So you have your negative differential because it is being used up, and that is equal to K times by the concentration of A. If you rearrange the differential, then you end up getting the change in A on left hand side, and you get the change in time on the right hand side. If that's a differential, and you may know it already, then we integrate on both sides. On the left hand side, we are integrating from the initial concentration of A until the final concentration of A. On the right hand side, we are integrating from T0 till the point T. And you may know that if you integrate a constant, then you get x, and if you integrate 1 over x, well, then you get ln of x. So we use that definition, and you end up getting an expression that looks something like this. So now you have ln of A minus ln of A, the initial concentration of A, is equal to the negative rate constant multiplied by the variable t. And if you rearrange it, then you end up getting the expression for a first order reaction. And it looks something very similar to the expression of a linear curve, that is y is equal to mx plus c. That would mean that the negative k times t, that would be your slope, negative k, that would be your slope, and the ln of the initial concentration of A, that would be your y-intercept. And if I was to plot the curve, it would look something like this. For a large k value, you'll see that the curve is a lot steeper, and for a small k value, the curve is obviously less steep as compared to a larger k value. And you would have your ln of A on the y-axis and time on the x-axis. Another way of writing that expression is that if you raised everything to the power of e, then you could rewrite that expression in terms of the expression on the right. So you have your concentration of A is equal to the initial concentration of A multiplied by the natural exponent to the power of negative k times t. Another important expression that we can get out for the first order reaction is that of something called a half-life. and that is the time it would take for the concentration of A to reduce by 50%. And that is mathematically described by A would be a half of your A0. So if you rearrange, then you end up getting that expression. Now, using the expression that we have on the left-hand side, if I was to write that up for T half, then I would get that. Now, since A0 cancel out, you will end up getting that expression. And then by using the natural logarithm, you will get that the half-life of a first order reaction is basically ln2 divided by k. The interesting fact is that the half-life of a first order reaction is independent of your concentrations. And that's quite interesting. So that means that it is entirely dependent on the rate constant, the K value, and independent of the concentration value. Now coming down to the second order reaction instead. A second order reaction is a reaction where the concentration is raised to the power of 2. And that could be something like this. In this scenario, our reactant is the same, very similar to the example that we looked at of nitrogen dioxide, where the same reactant is where the reaction is second order with respect to one reactant, and therefore we end up writing K multiplied by concentration of A to the power of 2. We will use the exact same method as before. So if you rearrange the differential, you end up getting that. And then again, we take the integral on both sides. And we know that if you integrate 1 over x squared with respect to x, you end up getting negative 1 over x. So keeping that in mind, you end up getting that expression. So you have 1 over A at time t minus 1 over A, which is the initial concentration, is equal to K times T. And by rearranging it, you will end up getting an expression that looks somewhat like this. And it again, resembles the same plot, the same equation for a linear curve, that is mx plus c. So once again, the slope of your expression would be k, the rate constant. And for the half-life of a second order reaction can be derived using the exact same method as before. I'm not going to do the entire derivation, but if you use the exact same derivation, then you would end up getting an expression of 1 over k times by the initial concentration of your reactant. So unlike the first order reaction, the second order reaction is actually dependent on your initial concentration of your reactant. But interestingly enough, because in the previous scenario, we said that the reaction is second order with respect to the same reactant. You can also have a scenario where you actually have two reactants. You have A plus B, and they're both with respect to first order. But if you remember from previous slide, that the order of reaction is the sum of all of your powers. So you can actually have a reaction, or you can actually have an order that is first order with respect to two different reactants, but the sum of the powers, that's still 2. So it's still a biomolecular reaction. And within that, there are two scenarios. The first scenario, the one that was very similar to that if we say that the starting concentration of A and B is exactly the same, right? Then there's no difference between A and B, because in terms of kinetics, they're both equal. So if the starting concentration of A0 and B0 are equal to each other, then we can rewrite that expression in terms of K times concentration of A to the power of 2. And that is exactly the same as the one example that we saw earlier. So there's nothing different in that. On the other hand, if the starting concentration of A and B is not the same, then you will end up getting an expression which is dependent on both A and B. So the rate law that you see on the screen there would be the negative differential for dA over dt is equal to K times A times B. So since we have two different reactants, then we would say that let X be the concentration of each species that has reacted at a time t. So that means that we can substitute small a, for A0 just to make the calculations a bit easier. And we know that after a specific amount of time t, X amount has reacted. So that would be your A0 minus X. That is your A value, the concentration of A after a specific amount of time t. And we write the same expression for B. And the reason it's both X and minus X for A and minus X for B, because they're both with respect to first order, right? And if they're both with respect to first order, that means that they're both getting used up in the same amount, in the same reaction rate. So coming back to the rate expression, the rate law that we had derived, we're going to insert the information that we have got. And since A0 is a constant, that means that we can rewrite the differential on the left-hand side as dx over dt. Because remember that if you differentiate a constant, you get 0, right? And it already has a negative. So a negative negative, that makes a plus. So then you would have a dx over dt is equal to k times delta A and delta B, where delta A and delta B, that is the expression A0 minus X. That is the amount of concentration that each species that has reacted at a specific time t. We will rearrange it just like before. So now we have all of our X components on the left-hand side and t on the right-hand side. So we have now come down to this one. We will substitute the original definitions, that instead of writing delta A and delta B, we'll just introduce our A0 minus X, B0 minus X, because we have to integrate on both sides. On the left-hand side, we will integrate from 0 until X. And on the right-hand side, we will integrate from 0 or T0 till T. In order to solve that integral, we have to make use of something called the method of partial fractions. I'm not really going to go and jump in detail, but that's something that you possibly can read up on it yourself, or maybe you probably already are aware of it. It's a very basic integration technique that you do learn at engineering school. So if you were to integrate that expression, we end up getting something that looks like this. And now we will introduce all of our original substitutions. So instead of B and A, we will use the notation initial concentration of A and the initial concentration of B. By doing so, and then by using the definition of logarithms, we end up getting an expression that looks something like this. And on the right-hand side, we just simply have K times T. And then if you simplify it or rearrange the expression, we will end up getting an expression that looks something like this. On the left-hand side, we have the natural logarithm of the fraction. On the right-hand side, we have K times the difference between the concentration of B minus O times by T. And that is the rate expression for a second order reaction. We do not calculate the half-life because it's actually quite complicated, because now we have two different reactants reacting in the reaction, and therefore it is not easy to model how long it will take for one of them to halve. So yep. And if you were to plot that curve, if you plot that, you will end up getting an expression that looks somewhat like this. And you'll notice that your y-intercept is actually 0. So therefore, if I look at y is equal to mx plus c, c is equal to 0, and therefore the slope would be equal to simply k times by b0 minus a0. So that is essentially how you make the mathematical models. These are like the most simplistic mathematical models that we get, but this is from where you start. Regardless of how difficult the problem is or how complicated the problem is, this is from where you would start if you are making the mathematical models for kinetics. And then if you plot your first order, zero order, and the second order reactions, then you would end up getting slopes that look somewhat like this, obviously. And these are all the derivations that we have done so far. So we will take one example as well. So imagine that a 5-gram substance decomposes for 50 minutes. The mass of unreacted species is found to be 0.5 grams, what is the half-life of this reaction if it follows first order kinetics? So you're starting off with a substance of 5 grams, you let it decompose for 50 minutes, and after 50 minutes, 0.5 grams is still remaining. So what exactly is the half-life? Assuming that we have a first order reaction at hand. So we will start off with the rate expression that we derived earlier. Ln of A is equal to minus KT plus ln of A0. You rearrange it so that you get an expression that looks something like this, because we're trying to solve for K. So if I take K to the left-hand side, then we get an expression of negative ln of A over A0 divided by T. We have all of our values. We put in all the values. So now I have calculated my K value. The K value is 0.0461 per minute. And then by using the half-life formula, which we also derived earlier, T is equal to ln2 divided by K. And then we know that it was 15 minutes. So it will take 15 minutes for the substance to reach its half-life. So that means after 15 minutes, it actually had reached the half of the reactant. So that's how you would solve a very simple problem for kinetics. In another scenario, let's say that how you would figure out the second order, the order of your reactant. So we have this example where you have nitrogen dioxide decomposing into nitrogen oxide and oxygen. Sorry. So now you have 4 reactions, right? For the 4 reactions, you have the concentration of nitrogen dioxide, and you have the initial rate. So if you look at experiment 1 and experiment 4, you'll see that between experiment 1 and experiment 4, the concentration of nitrogen is increased by 3 times. So in 4, it's 0.005. In experiment 1, it's 0.015. Increased by 3 times, and the corresponding initial rate was increased 9 times. And if you look at experiment 2 and experiment 4, then you'll see that if the amount of nitrogen dioxide is increased twice, not twice, but if it is doubled, then the initial rate is quadrupled. That means that every time the initial rate is increased by the power of 2. So that is why we know that the reaction is second order with respect to nitrogen dioxide. And that's how you would actually analyze the data and figure out whether or not the reaction is first order or second order. In a very simple reactions, given that you have the reaction in front of you. So, and that was all for the mathematical models and for the basics of kinetics. Now, just for closing remarks, we're going to very quickly talk about the relevance of kinetics in the industry. And kinetics are incredibly relevant for the industry. Obviously, like I said earlier, the Haber process for ammonia synthesis, by the use of kinetics, by the use of catalysis, we have been able to optimize the reaction for high pressure and temperature by using iron catalyst. If it was not for that, it obviously would have been very difficult for us to produce ammonia at that scale, and especially produce large-scale fertilizers. At the same time, in petroleum refining, catalytic cracking kinetics maximizes fuel yields and also minimizes the waste production. And these are like only 2 very basic examples that you'll see. The use of catalyst is almost widespread throughout the industry, let it be the pharmaceutical sector, the oil, petroleum refining, even material science. It's even in the biochemical sector, the use of catalyst is a huge benefit in order for us to be able to provide, be able to improve the yield, increase the yield, at the same time decrease the amount of energy and the money that is being spent on the process. Many of the other sectors where kinetics is really used could be environmental engineering, in food engineering, pharmaceuticals, material science, and even battery development. And like I said earlier, like climate change, for example, that's also a form of kinetics. Like how long, um, like the ozone layer depletion, for example, that is an excellent example, because there have been great deal of studies. You can even read that up on Google, on different books, on how we can figure out the reactants and the reaction that is increasing the depletion of the ozone layer and so on, and how we could possibly reduce it. How can we possibly reduce the effect of global warming? Uh, how could we possibly reduce improve the yield of pharmaceutical products while still controlling or reducing the production of byproducts, so that we don't have to spend that much money on the downstream processing. So you see, so these are a lot of considerations that do come up in the industry as something that we can make use of, and we can easily maximize by our understanding of kinetics. So that was all for free to wait. But thank you so very much for listening and for joining in today. It's truly appreciated that you made time to join us and listen to me speak and learn about kinetics. And I really hope that the webinar was helpful for you to get the basic understanding of what the kinetics is, and now you have a better understanding of the factors and the mathematical models. And do stay tuned for other webinars by Chemical Engineering Life, and you can visit our website at www.ChemEnggLife.com, where you can sign up and check out all of the other webinars that are up